Okay, guys, so we're gonna go over the FRQ from the Unit 3 test. Again, this is on the 2006 AP test. And so a lot of text. I'm not gonna go over the text with you guys, but let's just go to part A. It says this compound is analyzed for nitrogen content only, and the mass percent of nitrogen is 28.84%. It's asking you for the mass in grams of nitrogen in the original 1.2359 gram sample. So this one is talking about the original compound they're talking about. Now it tells you that the original compound is 1.2359 grams, and it's asking you what percentage of that mass is just nitrogen. Well, if this is the total, and it tells you that the total compound is 28.84% nitrogen, all you have to do is multiply this by 28.84% or 0.2884, and that's going to give you the nitrogen content. Okay, so you just punch that into your calculator, and you should get 0.36 grams of nitrogen. Okay, and this information comes from up here. Your original compound has carbon, hydrogen, nitrogen, and oxygen. It weighs a total of 1.2 grams. If 28% of that is nitrogen, well, just multiply it by the percentage to get the grams of nitrogen. Okay. And again, I am recording this, so if you miss out on anything, you can always go back and take a look at this. But do you guys have any questions on this part A? It's just percentage. Okay. All right, let's move on to part B. So for part B, it's asking you now. So like we said, the original compound is made of carbon, hydrogen, nitrogen, and oxygen, right? We just found how much of it is nitrogen. Now it's asking you for the mass in grams of carbon, okay? And it's telling you to assume all the carbon is used to produce CO2. So if you guys take a look at the original information, it tells you that you have this original compound. So I'm gonna scroll down. Does anyone still need this? Okay, I'm gonna scroll down a little, and you won't be able to see this, but I will be referring to this text portion. So yeah, just be aware of that. So it's basically telling you that you have this compound that's made up of some carbon, you don't know how much, some hydrogen, I'm gonna put a question mark, nitrogen, and oxygen. Okay. And then it tells you that it undergoes a combustion reaction. So you guys should know that combustion is when this reacts with oxygen, and it's going to produce CO2 and H2O. That's combustion. And then since there's nitrogen, there might be some other stuff, but we don't really know. It doesn't really matter. Okay. Does this part make sense? Why we get this information? Yeah. Tells you that it goes combustion, so plus O2, and it makes CO2. Well, this problem tells you that all of the carbon that was in the original compound is used to produce CO2. Okay, so all of the carbon that we had in our original compound goes into CO2, which means all of the carbon that was in this compound is going to have the same mass inside of CO2. Well, if you take a look above, how much CO2 does it say that the reaction produces? Yeah, if you take a look at that first paragraph at the top, it tells you it creates 2.241 grams of CO2. Everybody good with that so far? Okay. Well, if we know the mass of CO2, we can figure out how much carbon is inside of that CO2, right? We just need to do a little bit of dimensional analysis. So we can get our starting number of 2.241 grams of CO2. And if we just want to find the carbon in there, you could turn it into moles. So we can say 44 grams of CO2 in 1 mole of CO2. We know that in 1 mole of CO2, there is 1 mole of carbon. And then we know that 1 mole of carbon is 12 grams. So by using dimensional analysis, we can figure out how much carbon is inside our 2.2 grams of CO2. And since all of the carbon in CO2 came from this original compound, that's going to be the same number. So if you plug and chug that into your calculator, you should figure out that there are 0.611 grams of carbon inside your 2.2 grams. So 0.611 grams of carbon. And again, since all of the carbon in here came from here, that means there are 0.611 grams of carbon in your original compound as well. What's up?
Wait, so the reason we know it's a 1-to-1 mole ratio is that all the carbon dioxide.
Yes, that's correct. Yeah, it's this statement right here is the key. If you didn't have that statement, this problem would be impossible because you don't know what other stuff it would have made. Yeah. Good question. All right. Any other questions on that one? I know that one was a little bit tricky because you had to assume, or this part right here, you had to assume all of it went into the CO2, but from there, it's just dimensional analysis. All right. Hopefully this is kind of helping you guys understand it. Let's move on to part C. So for part C, now it's asking you to find the mass. Ooh. Sorry, that shouldn't be there. Okay, the mass in grams of oxygen, the original compound. Well, if we have the original compound, that's 1.2359 grams. This is your total. And we want to find oxygen. All we have to do is just kind of start taking away some information, some numbers. Okay, yeah. Yeah, that's the other one. Okay, so like we said, the compound is made of carbon, hydrogen, nitrogen, oxygen. You want to find the oxygen, and you have all the info for the other one. So we just need to subtract. Okay, we figured out from part A that we have 3.6 grams of nitrogen, right? Inside the original compound. In part B, we found out we have 0.61 grams of carbon. And then if you look at the original paragraph, it tells you that you have 0.356 grams of hydrogen. So all you got to do is just take away nitrogen, carbon, hydrogen, and that gives you oxygen, which should give you a total of about 0.2 grams of oxygen. So close. So close to getting it right. You would have been the only one. Not you, Kayla. Kayla literally forgot a 0 and then she got like half a point off. So close. Or maybe it's because I had a vendetta against you. I erased a 0 and messed you up.
No, but
I did.
had I not thought it was a ratio.
Yeah. That was good. There were some really good attempts, which is why a lot of people got partial credit.
Yeah, I think I was like, I almost had the back.
All right, guys. So I'm not going to go over part D completely with you guys, but I'll kind of give you guys a starting point. Hopefully you guys are familiar with the empirical formula. You just need to take the grams of everything, and you just need to turn them all into moles. So you take your 0.36 grams of nitrogen, turn it into moles of nitrogen. Same thing with the other ones. So you turn all of these into moles, and then that gives you your empirical formula. So I'll actually give you the final answer. For test corrections, you do need to show the work. So this is just so you can check your work at the end. But the final empirical formula will be C4H5N2O. Okay, this will be your final answer. And again, turn it into moles. You plug it into the equation, divide by the smallest number. It's that empirical formula stuff. And did you have a question? Yeah. So again, make sure you show your work, try out the problem, but you should end up with this right here. Okay, so again, this is 4.5 in the workbook. See if AgNO3 and KCl, if combining them can produce a precipitate or not. So I'll give you guys maybe about 2 minutes to try that out, and then we will move on. Yes.
Is the 61 passing?
Huh?
The 61 passing?
For what?
For a test?
It depends on the year for the AP test.
For like on that test.
I guess. I don't know. Okay, so let's go over 4.5. So we got AgNO3, so that's our first compound. And then we have KCl, and then we're gonna do a double replacement, and that's gonna form AgCl and KNO3. Okay, so we're going to be checking if AgCl and KNO3 are soluble or not. So let's start with AgCl. Is AgCl soluble? No, it is not. If you look at the chart, if you look at AgCl, we got Cl, it is soluble usually, unless it bonds with Ag. So AgCl is insoluble. So this is going to be your precipitate. Okay, and if you guys remember, KNO3, anything with nitrate is going to be soluble. And also anything from the alkali metals is also going to be soluble. So this guy is always soluble. It's made out of two soluble things. Okay. Double soluble. Yes. All right. Any questions on 4.5? Easy peasy. Okay, let's move on. So what we're going to be doing now is we're going to be learning something called ionic equations. So you guys are familiar with regular chemical equations, but when it comes to working with solubility and ionic compounds, there's other types of chemical equations you'll have to be familiar with. This isn't going to be super important now, but once we go into the later units like that have to do with acid base, I think it's like unit 12 and 13, this will become super duper important. But anyway, so this right here, if you take a look at it, this is what a general chemical equation we're familiar with looks like, right? It tells you what the chemicals are. It tells you if it's aqueous or if it's a solid. Okay. Now this right here is called a molecular equation. So I want you to just write that term down, molecular equation. And you can just denote a molecular equation as just a regular chemical equation. So make sure you write that down. A molecular equation is what we're used to working with. It's just a regular chemical equation. But unfortunately, when it comes to ionic compounds, there are two other types of chemical equations we gotta learn. So we can actually take this equation right here, the molecular equation, and we can write it two different ways. Okay. So that's what we're going to be learning in this section. Isn't this exciting?
Yes.
No, it's not. All right. So the first type of equation, the other one, other than the molecular equation, and I want you guys to write this term down, is called the complete ionic equation. A complete ionic equation. And in a complete ionic equation, you separate all of the ions. So if you take a look at this right here was what we had earlier. We had PbNO3, and then we just split it up into the ions. Right? We had Ki, we split it up into the ion, and so on and so forth. So in a complete ionic equation, you just need to split up all the ionic compounds into their constituent ions. Okay. That makes sense? Hopefully. All right, now there is one thing I do want to mention is that if something is a solid, if something is a precipitate, you do not split it up in a complete ionic equation. Okay, you don't split up the solids. And the purpose of this equation is just to show you, hey, how do these chemicals actually function inside of water? What do they actually look like in terms of their chemistry? Okay, so one other useful thing about the complete ionic equation is it tells you what ions don't do anything, which ones don't change. So let's take a look at all of the ions on the left side and see how they change on the right side, okay? So if you take a look at Pb, it starts off dissolved in water, right? It's aqueous. But on the other, once it reacts, is it still aqueous? No, it's a solid. So Pb is actually going to change forms. It's going to change forms from aqueous to solid. Okay, but if you take a look at nitrate, nitrate is aqueous on both sides, right? Which means it didn't really do anything from a chemical perspective. It was aqueous And then it's still aqueous. So if you think about it, this guy is pretty useless. Okay, and these useless ions are called spectator ions because they don't do anything. They just spectate. They're like me and the NBA. I just watch and I complain to the refs. Like, that's not travel. That's not a moving screen. It's not a moving. Warriors don't set moving screens, okay? Yeah, that's what I am. Dude, you guys get more foul calls than anybody, dude. If I fart in LeBron's general direction, you guys get a foul and free throws. Get over it, dude. Hey, start grading, TA. All right, finish the whole stack. Yeah, okay. All right. Does that make sense, guys? What spectator ions are? Spectator ions are Mr. O on the couch watching basketball. He doesn't do anything. He's aqueous on the left side, aqueous on the right side. Yeah.
So is potassium also a spectator ion?
That's correct. Potassium, if you take a look at it, is aqueous on the left and the right. So potassium is also useless and is also a spectator ion. So if you guys take a look at the only ions that actually do anything are lead and iodide, right? So what we can do is we can write something called a net ionic equation. And in a net ionic equation, all you're doing is you're writing the ions that actually do something, okay, which are Pb and I. Okay, so those are the three types of chemical equations when it comes to ionic compounds. You got molecular, which is the normal one. Complete ionic is where you split up all of the aqueous ions. And then a net ionic is where you write only the stuff that does something. Okay. That's it. Those are the three types of equations. And then now we're just going to practice writing them. You guys think you could try it out?
Yeah.
Okay. All right. We'll do one together and I'll have you guys try some on your own. But let's do 4.6 together. And what we're going to do is we're going to write the molecular, complete ionic, and net ionic. And we're going to figure out the spectators. So 4.6, you're going to have to be comfortable with writing the names of the ionic compounds, which I know that you guys enjoyed doing. So let's start with calcium chloride. What is the symbol for calcium? Okay. And then chloride is? Okay. Now to balance the charges, where do I add a number?
To the chlorine.
Yeah, to the chlorine. Calcium is +2. Chlorine is -1. That's hard to see. And so we want to balance that out. Okay, so that's calcium chloride. And again, calcium is +2. Chlorine is -1. Okay. Let's move on to the next one. The next one is sodium carbonate. So sodium is Na+. So this one is +1. And then carbonate is CO3 2-. So how many sodiums do we need to balance out the carbonate? 2. Yeah, piece. Okay. All right, so I will give you guys a minute. See if you guys can finish up the molecular equation. See if you guys can figure out what the two compounds are. And then after that, I want you guys to tell me which ones are aqueous and which ones are solids. Okay, take a second to do that, and then we'll go over it. All right, is calcium chloride aqueous or solid?
Wait, calcium chloride. Oh, it's solid. It's a solid. Get it. Solid.
Insoluble, right?
It is soluble. It's because it is soluble. It's the only exceptions are Ag, Hg, and Pb. Okay, so the first one is going to be soluble. So AQ. All right, let's go to the next one. Is this one aqueous or soluble? Or solid, sorry. Aqueous or solid? This was aqueous, and we know that because it has sodium. Sodium can't commit. It can't become a solid. Sodium is Taylor Swift.
Damn.
What's up?
But how do we know that calcium chloride was without the sheet?
Yeah, that one you would have to look at the sheet.
Okay.
Okay, let's do our double replacement. So calcium is going to react, they're gonna switch because they both break up. Okay, so calcium is going to react with carbonate. And you're gonna get CaCO3. Now, is this going to be soluble or solid?
Solid.
This one is a solid. Yeah. Okay. And then you have Na, which reacts with Cl, which is going to be aqueous. It is salt, yes.
Both of them make a precipitate.
Yeah. You'll have a bunch of chunks in there. Yes.
But when looking at the chart, it said it's insoluble, but then there are exceptions. It's under insoluble, but it has exceptions.
Yes. It's like a double negative. Yeah. Yes. All right. Everybody good with these?
Yeah.
Make sense? Okay, so that's the molecular equation. We do need to balance it though. So we just put a 2 right here. That's it. Yeah, just put a 2 in front of knuckle. All right, guys. So from there, we're gonna write the complete ionic equation. So for the complete ionic equation, you just need to break up everybody into their ions. So I'll do this with you guys, and then for the next example, I'll have you guys do it. But you got Ca, which is Ca2 plus. You have 2 chloride ions, which are minus. Okay. And then you have your sodium. You have your 2 sodiums, which is going to be Na plus. And then you have your carbonate, which is 2 minus. Okay, and that's where your arrow comes from. And since they were all aqueous, since these 2 are aqueous, all of these guys are aqueous. All right, now I'll give you guys a minute, see if you guys can do the right side of the arrow, see if you guys can split those up into their ions. And again, you don't split up the solid. So take a second to do that. And then after that, if you feel like you can do the net ionic, try that out. But we'll go over that in a second. Okay, so for the right side of the arrow, the product side, you should just get CaCO3. And this one stays together because it's a solid. You don't split this guy up, okay? And then the other one, you're going to get 2 Na plus ions, and they're both going to be aqueous. And then you're going to get 2 Cl ions and those stay aqueous. Okay, remember that you need 2 NaCl, so you're going to get 2 of each of the ions. Okay, so that was kind of where the trick was. Okay, so that's your complete ionic. All right, so let's figure out what the spectator ions are, the ones that don't really do anything. So what's our first spectator ion? Yeah, the chlorine is going to be one of our spectators, and then I heard the other one as well. The other spectator ion is going to be our sodium. These are our 2 spectators, because if you take a look at them, they don't do anything. They just stay aqueous on both sides, right? So they're pretty useless. Okay, make sense? All right, let's move on to our net ionic. So finally, for our net ionic equation, all we have to do is write down the useful ions, the ones that change, which is going to be Ca2 plus, aqueous, plus CO3 2 minus, which is also aqueous. And then they do change their solubility into a solid. And there you go. Those are your 3 types of equations for ionic compounds. Alrighty, guys, let's move on. Do you guys think you could try one on your own? Yeah. Okay. I'm gonna give you guys about 5 minutes. See if you guys can do number 4.7 on your own. It might be kind of hard to see up there, but you should have it on your screen. But try 4.7. See if you can work with the person next to you and see if you can get all 3 types of equations and identify the spectator. So this is like your test to see if you guys can do all 3. So I'll give you guys about 5 minutes. I will give you guys a heads up. There is going to be a question on your exam that has to do with this thing right here. So yeah, try it out. All right, so let's go over this one. So silver 1 nitrate. I'm just gonna give you guys the equations. If you guys have any questions about it, please let me know. But silver 1 nitrate is AgNO3, and since it has nitrate, that's gonna be aqueous. And then for the next one, we have potassium phosphate, which will be K3PO4. And since it has potassium, it's going to be aqueous. She said that. You should have listened. Okay. All good with that?
Yeah.
All right. We're going to go switcheroo. And then we'll get Ag3PO4. Huh? Yeah, I gotta finish the equation to balance it.
Oh, yeah, you're right.
Ugh, rushing me. Okay, AgPO4 is a solid. Okay, and then we'll get KNO3, which is gonna be aqueous. Okay, and as I've been told
My bad.
That's
my bad.
prematurely, and you need to balance it. So you put a 3 here and you put a 3 here. I'm just messing with you. All right, and that's gonna be your complete answer for the molecular formula. Okay, am I missing something? What? It's necessary. You need to balance it. Yeah. Does it make sense though? Even if you gotta correct some stuff. All right. Let's move on to what's the other one? Ionic? Complete ion. Thank you. What would I do without you guys? All right. So you got 3 Ag pluses, which will be aqueous. You have 3 NO3 minuses, which are also aqueous. You have 3 potassium ions, which are also aqueous. And then you have your phosphate, which is aqueous. Okay. So I guess the tricky thing here is just remember the 3 is going to apply to both your Ag and to your NO3. Okay. For your product side, you have Ag3PO4, which is your solid. And then you're going to have 3 potassium ions, which are aqueous. And then you'll have 3 NO3 minus ions, which are also aqueous. There you go. That is your complete ionic. I hate chemistry.
Dude, I love chemistry. So why did he make sure it's
Hmm?
it's so
I don't know.
I'm so happy whenever so what's for chemical physics.
Neither. Games.
Like, we like one.
Guys, I just want to go home and play games right now. I'm still thinking about it. All right.
I'll teach the class.
No. Okay. So for your spectators, you should have gotten NO3 nitrate and potassium as your spectators, because if you notice, on both sides they're aqueous. Okay. Those are your spectators. All right. And then lastly, yes.
For the non-spectator.
Exactly. Yeah. Exactly. So that's a good question. Next, watch. Next time you ask you a question, I'm gonna shame you for having a question too. No, Jordan's gonna be like, what's your name, Mr. You don't even know? All right. Anyway, so your net ionic will be 3 Ag ions and 3 potassium ions. Oh, sorry. Whoa. I'm having a stroke. Sorry. You have your phosphate.
Oh,
Wait, you haven't what?
Dude, sometimes my brain just like bugs out.
Should just take it.
There we go. Whoa. Sorry guys. I was like, whoa, okay. You have that for your net ionics. You got 3 silver ions. You got 1 phosphate ion forming Ag3PO4. Okay. All right, and that's it. And again, I guarantee you that there will be a problem on your exam where you have to be able to do this. I guarantee.
Charles Barkley.
On this test. I can't guarantee anything on the AP test because I don't write it.
Oh, you don't make Charles Barkley? He always makes the shittiest like predictions.
Okay, guys, we're gonna quickly go over one more thing before we wrap it up. We're gonna go on to something called neutralization reaction. So acids and bases are a part of this unit, but it's also a huge part of the AP test. I think about 30% of the problems on the actual AP test have to do with acid base. And we're gonna kind of dip our feet into that right now. And then we'll get more into detail later in the school year. But let me just introduce you guys to acids and bases, okay? So I do need you guys to write these definitions down. I'm gonna paraphrase them up here for you if that's helpful for you. But basically acids, easiest way to think about acids, there's a lot of different definitions, but acids are substances that release, so think of it like this, they release H plus. Okay. Acids are substances, chemicals that release H plus. We're going to talk about different definitions for acids later, but in terms of the AP test, just knowing acids are the ones that release H plus, that's the easiest way to understand acids. Yes. Not necessarily. So I'm gonna talk about it. Yeah, I'm gonna get to that. I'm gonna get to that, okay? Okay, so they release H plus. And spoilers, they can release more than one.
How many?
Depends on the acid. Depends on the acid. Okay. So far, so good? So, different acids can release different amounts of H plus. Okay, so for example, you have this right here, HCl. How many H's does it have? One, so it can release one. These are called monoprotic because they can release mono, one. That sounds really bad. They can release mono. All right, they can give one H plus. Okay, there are other acids like H2SO4, which have two hydrogens, and they are considered diprotic because they can release di, so two. However, they have to release it in two steps. So they don't release two H's at one time. So you got sulfuric acid right here. It releases one H plus and it becomes HSO4 minus. And that guy can release another H.
Only kind of.
Kind of, yeah. Yeah, good note on that. They can only kind of do it.
So you said it was first H, HSO4.
Mhm.
Where did that H come from? The H?
This one, in solution.
That's not.
It's like floating around in the water. Yeah.
So that's why it has like the arrows going back and forth.
Yeah. Yeah. So H2SO4 is a strong electrolyte because it almost 100% of them will give up the H plus. However, the byproduct, HSO4 minus, they only kind of give it up. Okay. So that's the next point, right? But just keep in mind, for now, the most important thing I'm going over is acids, they release H plus. Okay. All right. Everybody good with that definition? Okay. So the opposite of acids are compounds called bases. Okay. And bases are a little bit trickier to define. There's two definitions you're going to want to know. The first is bases. Okay. They're like acids who give up H plus, but bases, they release OH minus. They release me. Okay, they give up hydroxide.
That's a perfect name.
I do. And I'm negative, dude. Imagine if I was a happy person, it would ruin everything.
That's like the most poetic thing I would.
It's a curse. I was destined to teach chemistry, and my children and their children and their children will all teach chemistry.
Well, what if you have like girls? So that's like
Girls can teach chemistry.
No, I know, but like.
Oh wait, they might change their names. Yeah. Well, never mind then. All the males in my family are destined to teach chemistry. Okay. So bases, one definition is they can release Mr. O. The other definition, so there are some bases that don't contain me. So for example, I am not within ammonia. But ammonia is a base because the other definition is that they can accept H plus. Okay, that's the other definition. Those are my cousins. Okay, so one type of base is compounds that release OH minus. The other type of base are compounds that accept hydrogen. Now, for the AP test, it's usually going to be ammonia, NH3. So just remember that NH3 is a base and it produces ammonium by receiving H from around it. All right, any questions on the definitions on acids and bases? Okay, again, we'll go super into detail towards second semester, so you don't have to be like an expert on this, but just keep those general definitions in mind.
How does it have like for the second?
It's not a strong electrolyte. Yeah, that's why. Yeah, so it's constantly, so these back and forth arrows mean equilibrium, which means if you have it in real life, the molecules are constantly absorbing, releasing H plus. We have a whole unit on equilibrium, so don't think too hard about it yet. Yeah. All right, so far so good. All right, now we're going to talk about different types of acids and bases. So we talked about how there's strong electrolytes and weak electrolytes, right? Same thing with acids and bases. There are strong acids and weak acids, and for bases as well. Okay, so let's talk about strong acids and strong bases. So we learned strong electrolytes, they completely break up inside of the solution. That's what strong acids and strong bases are. They are acids and bases that completely break up when you put them in water. Okay. And then same thing with weak electrolytes that kind of break up. Weak acids and weak bases, they kind of break up in water. Okay. So you got a list right here. You do have to memorize this, unfortunately, for the AP test. Okay, but I will teach you guys a very easy way to remember these strong acids and strong bases, okay? So I want you guys to take a look at your periodic tables real quick, and I'll teach you an easy trick to memorize strong acids, strong bases. Yeah. Yeah, weak acids partially release H plus. So not all of the weak acid molecules give up H plus. Same thing with the weak bases. They only some of them give it up. Whereas strong, they completely give it up. All right. You guys ready for the little trick to memorize these things?
Yes.
Okay. Yeah. So let's take a look at the periodic table, and then I'll show you guys my trick, okay? So we're gonna start with the bases. We're gonna start with the strong bases. I'm gonna do that in blue. So strong bases. So the strong bases are very simple. First column, second column, but we start at calcium. Okay, yeah, these are strong bases. And then you just need to add OH to it. So for example, lithium is +1, so you add 1 Mr. O, LiOH, that's a strong base. Next one, or let's start with calcium. Calcium is +2, so you need 2 Mr. O's. That's it. Those are your strong bases. Easy to remember. Just remember it starts at calcium. Yes.
But the first column starts at
Yes.
Okay, so the left column is all at one. So right column.
That's correct. Yeah. Because of the MCI +1 and +2. That's it. That's strong bases. So strong base is really easy. All right. And then we'll end with the strong acids. Okay, so strong acids are where it's pretty easy, but there are some things you got to remember. So let's go to the strong acids. Strong acids are going to be on the right side, and then you're going to look at chlorine, and you're just going to go down to bromine and iodide. So these three are your strong acids on the periodic table. Okay, so they're all kind of together. There are a couple you do need to memorize, and these are the polyatomic ones. The ones that you need to remember are going to be chloric, so HClO3, perchloric, HClO4. You got nitric, which is HNO3, and we got sulfuric, which is H2SO4. So those are the ones I guess you got to spend a little more time remembering. But just keep in mind, those are the strong acids you have to know for the AP test. But, let me preface it with one thing. Spend more time doing practice problems and memorizing this. It's worth more of your time to actually learn how to do the problems and do more practice and to sit down and memorize this. Okay. For AP Chem, memorizing should be like your lowest priority. Doing as many practice problems as possible, that should be your highest priority because that's how you'll pass the test. If you just sit and memorize, it's not gonna help too much.
How does the 1H plus balance with all the Cls?
Those are polyatomic ions,
Oh,
and they have a charge of -1, except for sulfate, which is -2.
but wouldn't that be like -6 Cl?
You're adding up the MCIs, but that's not how polyatomics work. Yeah. Good question though. All right, guys. So we'll end it right there.